Hello everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and discuss a very important theorem that has so many applications in the realm of numerical analysis and approximation theory, and it's called the Weierstrass Approximation Theorem. So what does this wonderful theorem tell us? Well, one of the first things that we need in order to build this approximation theorem is to get a little bit of motivation about how to approximate functions, and one of the easiest mechanisms to do that is what is called a step function. So what exactly is this step function? So we're going to be taking a real interval as the domain of our function. So for example, closed interval 0, 1, open interval 0, 1, any interval will do. Then we're going to say that fs is a step function if the range of that function is a finite set. So what exactly is a finite set? Keep in mind, it's always going to be a discrete subset of the natural numbers that is bounded above. So let's look at a very basic example to sort of show how a function is or is not a step function. So let's assume that we're going to map the closed interval 0 to 2, so we've satisfied the first assumption that we have an interval as our domain. And let's assume it maps to the set of real numbers, and let's assume we choose our mapping f of x to be equal to our x squared. So is this function a step function? So in order to determine whether it is a step function or not, we need to look at the range. So we should be able to easily verify that the range of this mapping is going to be equal to the closed interval 0, 4. And we already know that this set is an uncountable set. Right? It's an uncountable set because one should be able to show that 0, 1 is an uncountable set using the nested interval theorem, and obviously 0, 1, 1, 2, 2, 3, and 3, 4 are also uncountable, and we have a union of uncountable sets, which is obviously uncountable. And from here we have that this is definitely not a finite set. So if that is the case, that means that f is not a step function, right? So sad day for the parabola. So let's see if we can prove another example. Let's assume again we map the interval 0 to 4. Let's make the right endpoint open. And let's assume again we're mapping to the set of real numbers with the mapping f of x is equal to the floor of x. So is this a step function? So what exactly is the floor of x? So the floor of x is often defined as the following. So if we have any number between 0 and 1, we're just going to round down to the nearest integer. So this is going to be equal to 0 for any x 0 less than or equal to x strictly less than 1. It's going to be 1 for 1 less than or equal to x less than 2. It's going to be equal to 2 for any 2 less than or equal to x is less than 3. And it's going to be equal to 3 for any 3 less than or equal to x less than 4, right? And we're not going up to 4 because 4 is not included in our interval. So this is going to be our piecewise function representation of f. So if we look at this particular function in the graphical manner, what we have here is closed circle, open circle, closed circle, open circle, closed circle, open circle, closed circle, open circle, where these boundary points are located at 1, 2, 3, and 4. So this function looks like a bunch of steps, right? Because notice that this is practically just a vertical line. So it's just a bunch of steps that you probably would walk on. So is this function a step function? So what do we need to do in order to formally label this function as a step function? Well, we need to look at the range. So the range of this function is the discrete set 0, 1, 2, 3. Obviously a cardinality of 4, which is a natural number. So obviously this is indeed a finite set. So that means this function f is indeed a step function, right? So it's a happy day for the floor function. So now we know what a step function is. So now that we know what a step function is, let's introduce our very first and actually pretty important theorem. So theorem 1 says the following. So suppose that D is a closed and bounded interval. Let's assume that f has a domain of that closed and bounded interval, and let's also assume that f is continuous on that domain. So one of the previous theorems that we had before is if we do have a continuous function on a closed and bounded domain, this function is also uniformly continuous on that interval. So that's actually pretty interesting. So if we do have a continuous function on a closed and bounded interval, what do we have at our at our advantage. So if epsilon is any positive real number, then there always exists a step function, let's call that step function f of s, such that the distance between f of x and fs of x is always arbitrarily small, i.e. I can always approximate f with step functions to any degree of accuracy that I desire on the entire domain. So, okay, well, it's not necessarily a continuous approximation, but it is indeed an approximation. So let's see if we can actually prove this very wonderful step function approximation theorem. Not quite Weierstrass, but it's definitely in the right direction. So, proof. So what we're going to do is we're going to assume, let's actually give a name to our closed and bounded interval. Let's assume that D is equal to closed interval AB. And let's assume, without loss of generality, that obviously B is greater than A. If B is equal to A, then that's not very exciting now, is it? And let's assume that F maps D to R with F continuous on this closed and bounded interval D. Right? So what do we have in terms of assumptions? So we have that F is continuous. So F is continuous on a closed and bounded interval. So that much is given to us. So since f is continuous on a closed and bounded interval, that means that f is uniformly continuous on that closed and bounded interval. So if it's uniformly continuous on its domain, then what do we have? So that means for all epsilon greater than 0, there exists a delta greater than 0 such that if x and y belong to its domain with the distance between x and y arbitrarily small, then the distance between f of x and f of y, their images, is also arbitrarily small. So that's practically just the definition of uniform continuity. So if that's the case, then what do we have? So since delta is a positive real number, then by the Archimedean principle, what do we have? That means there exists an n in the set of natural numbers such that 0 is less than, we can call it 1 over m, is less than delta over b minus a. Now, I know I'm just focusing on delta in the precursor of this statement, but if b minus a is a real number and d is a real number and notice b is greater than a, that's also a positive real number as well. So I can use my Archimedean principle on the number delta over b minus a if I desire, right? So if I rearrange this Archimedean principle existence statement, that means that 0 will be less than b minus a over m, and that's going to be less than delta. Right, so obviously here we have some positive real number, and I'm going to be calling this number h. So if you've done any Riemann integrals for integral calculus, this h should look very familiar to you. All right, so once we have our h, which is obviously an element of the positive reals, what are we going to do with this? So now we're going to partition. D into n intervals of the same size. And the size or length is going to be equal to h. Sometimes we call this a uniform partition of D. So what will our partition of D look like? So D is going to be equal to, so we're going to start with the left, so we're going to start with A on the left and B on the right. And we're going to just break this interval into a bunch of pieces. So we have A here and B here. And we're just going to cut this into a bunch of pieces of the same exact length. So the first piece is going to be equal to, this is going to be a special piece actually. It's going to be A and A plus H, and it's going to be closed on both sides. And then for everyone after, we're going to be doing open on the left, so there's no overlap. So we're going to have A plus H, and then A plus 2H closed on the right for this one and the rest. And we're going to continue all the way down to A plus K minus 1, H, then A plus KH, so that's the general term. And that's going to continue all the way down to the last one. And what will be the last one? Well, the last one will actually be equal to what would that be? A plus n minus 1 h, and then a plus nh. And here, a plus nh is actually the same thing as b. All right? And here, this k, this general term, ranges from 1 to all the way down to n. All right? So that's going to be our general interval. Right? So this is going to be equal to our I1. This is going to be equal to our I2. This is going to be our general interval IK. And this is going to be our last interval IM. So let's just do a quick notation thing. So let's define IK to be equal to this interval AK, BK. I'm using curly braces on this left because it does switch from close for the first and open for the rest. So this is going to denote whichever one is appropriate for this particular k, where k ranges from 1 to m. So if this is the case, then what is the length of each of these intervals? So the length obviously is going to be equal to h by construction. So our distance is going to be equal to h, and by the Archimedean principle, we were able to show that that's less than delta. And keep in mind, this is going to be true for all k is equal to 1, 2, all the way up to m. So if that is the case, then what do we have? So that means that f of x minus f of y is going to be less than epsilon, and that's going to be true for all xy inside of ik. And that's going to be true also for all intervals ik. So if you pick any two elements, x, y, inside of the intervals, as long as you're inside the same interval, then the distance between them is always going to be less than delta because their distance is at most h, and therefore the image part of the uniform continuity assumption is going to be met for those particular x's as long as your x's and y's are chosen between the same exact numbers. So now we're going to start defining our piecewise function for our interval. So this is the big part. So we're going to define fsx to be equal to f of a plus kh for k is equal to 1, 2, all the way down to n, and this x value belongs to ik, whichever k we're sort of interested in. And if you remember the general form of our intervals, this is just going to be equal to the right endpoint of ik. Okay, so if we look at a particular picture to sort of get an idea of what we're doing here, so let's assume that we have this particular function, and let's assume that we're partitioning, for example, 1, 2, 3 intervals. So we have a and b, and this is n is equal to 3. So if we're just taking the right endpoint of this, then our step function is going to be equal to this function here, this function here, and this function here, right? So that's our step function approximation for this function, arbitrarily, of course. So that means if x belongs to ik, then the distance between f of x and fs of x is going to be less than epsilon for our particular element x that belongs to ik. And that gives us practically what we want because now we're approximating our function with an arbitrary step function constructed by using the right endpoints of our interval images, right? So that's actually pretty useful. But the only downside is this approximation that we're using for our function is not continuous, or likely not continuous, at the endpoints of our subintervals, which can be a downside. So the question is, okay, well, we can approximate any function with step functions, but can we do a little bit better, maybe even build a continuous approximation? So let's actually go through a quick investigation of how one would do that. So the next question that we're going to be investigating is, how can we do a little bit better than step functions? So if we think about the graph of some random function, let's assume we have like this bell curve, Gaussian type of distribution, and let's assume that we take these points as our subintervals a, b, right? Obviously, we're going to be projecting onto this curve. So there's our potential endpoints. And for our approximation for step functions, what we had was this one, we had that one, we had that one, and we had that one. So obviously it's very far off, especially if the curve is changing a lot. So what is better than this? So keep in mind for the step function approximation, at least the one I'm drawing here, we're only required to use 1 point in each of those subdomains, but you can obviously do like the midpoint or something like that if you really desire, or some hybrid method on different intervals. Now, what's better than this? Well, if you think of step functions as degree 0 polynomials, we obviously would be motivated to go up to a degree 1, like a line. So if we go up to a degree 1, this is what some people refer to as a piecewise linear approximation. And this needs or requires 2 points. 2 points. So if we sort of take the same exact curve and use a linear extrapolation method, what we're going to do is we're just going to be connecting these points with one another, and obviously those lines appear to approximate the curve a lot more compared to our piecewise function, except for probably this region in the picture right here, right? But practically everywhere else it appears to be pretty decent, at least with respect to my horrible drawing skills, right? And obviously, how would you go a little degree up? So what would be higher than a line? Well, that would be a piecewise quadratic. A piecewise quadratic approximation, and that is going to need 3 points. So how would you do 3 points? So let's actually draw a new picture here. Let's sort of illustrate how a piecewise quadratic method will work. Let's assume that we have this type of curve here. Let's actually go on a wider interval now. Let's do this one, 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 this one. So what we're going to do is we're going to project upwards and find the image of this curve at all of those points. And then we're going to go from left to right and choose 3 points. So we're going to approximate the first 3 points with a parabola. Let's call that P1. And then we're going to do the next 3 points with a parabola. That's going to call, let's say, P2. And then we're going to approximate these with a parabola. That's going to be P3. And then we're going to have the next parabola here, P4. And notice, at least in my picture, I only have practically 3 more points, which actually covers the domain quite nicely. So it's very trivial to say that this would be your P5. But if you were to have, like, say, another point here, obviously you do not have 3 points, you just only have 2 remaining. You can always go a linear approximation for your remaining 2 points in order to get your approximation there. So that's practically what your parabolic approximation looks like. And the only real issues that one may observe is that it's not really smooth where your parabolas meet. So obviously, if you have a smoothness requirement, you may want to go even up to a degree 3 interpolation, still require only 3 points, but have your 4th degree of freedom be associated to smoothness. Now, let's actually go through a numerical example of how one would actually construct a parabolic approximation to a curve. Let's actually choose a very famous curve that everyone should know, and that's going to be the sine function. So let's assume we have the interval 0, pi over 2, with the mapping f of x is equal to the sine of x. And let's assume that we want to approximate this with a parabolic approximation. So what would that look like? So if we draw a graph of what our sine function looks like on the interval 0 to pi, we have this shape, and here would be our pi over 2 value. So if we just do one interval with a line, obviously it's not going to fit that great. So that's why some people will be motivated to use 2 subintervals, and let's fit a parabola onto it, because now we have our 3 points, and our parabola should fit pretty well to that curve on the interval 0 to pi over 2 anyway. So our points are going to be as follows. So our points are going to be equal to 0, 0. That's the first one. And then pi over 4, and the sine of pi over 4 is going to be the square root of 2 over 2. So that's going to be our second point. And then our third point is going to be pi over 2 comma 1. So that's that point on the top. And what we're desiring is to have our first piece and only piece to be equal to the form ax squared plus bx plus c. So we have 3 points. We have 3 unknown constants that we need to find in order to find this parabola P1 that approximates this curve on the closed interval 0 pi over 2. So let's create a system of equations. So using the first point, we're going to have a 0 squared plus b times 0 plus c is equal to 0. So this is for the point 0, 0. And then we're going to have a pi over 4 squared plus b times pi over 4 plus c is going to be equal to the square root of 2 over 2. So that's your pi over 4 square root of 2 over 2 point. And then we're going to have a times pi over 2 squared plus b times pi over 2 plus c, and that's going to be equal to 1, and that's going to be your pi over 2 comma 1 point. And this is obviously a system of 3 linear equations, 3 unknowns. And let's just quickly write this in matrix form because this sometimes is a little bit more annoying to work with, so you probably use solver to solve this. So once you simplify, this is going to be 0, 0, 1, and then pi squared over 16, pi over 4, 1, and then pi squared over 4, pi over 2, 1, times ABC is equal to 0, square root of 2 over 2, and 1. So what we have here is some coefficient matrix A, our variable vector x, let's call it. Let's put a hat there, not to confuse with the x before. And then we have our constant coefficient vector B. So what we need to do is we need to solve this equation for x, and obviously we need to be able to find the inverse of A, so x hat will be equal to the inverse of matrix A times that vector B. And as long as this determinant of A is not equal to 0, then we're going to be safe. So one can find, at least numerically or using whatever methods you have for determinants, this is going to be equal to approximately negative 2.9, which is obviously not equal to 0, which means we have a unique solution x hat for this matrix equation. So once you actually find your matrix A inverse and multiply it by your vector B, then you're going to have your numerical solution. And one can find using, either by hand or, with computer software like R, MATLAB, or Python, or whatever you prefer to work with, your solution vector ABC is going to be approximately equal to negative 0.1119, 0.9882, and 0. And that 0 shouldn't be surprising because we're passing through our origin, which means we have a y-intercept of 0, and that's practically what that corresponds to at the end, right? And it's going to be facing downwards because that's practically the behavior on 0 pi over 2, so that's obviously going to be equal to negative. So what is our parabolic approximation for sine of x on 0 pi over 2? So that means that p1 of x will be approximately equal to negative 0.1119 x squared plus 0.9882x plus 0, and that's our approximation. And what is this approximation for? So this is going to be approximately equal to sine of x as long as x is between 0 and pi over 2. If you go outside of this interval, you're not guaranteed any accuracy whatsoever, but as long as you're between these two numbers, then this is at least up to what we call degree 2 accuracy for our approximation. So now it's time for the big moment. The first theorem that I want to talk about now is what we call the Bernstein Approximation Theorem, and it says the following. So if we have the closed interval 0, 1 as our domain, and let's assume that we're continuous on the domain, then there always exists a natural number n in the set of natural numbers such that if little n is bigger than big N, then the distance between f of x, our continuous function, and some other function notated by b subscript n of x will always be less than epsilon for all x is in the closed interval 0, 1. So now we're not approximating fx with a step function, we're not approximating it with a line, now we're approximating it with this object b and x, where b and x can be represented as this summation. So we have n choose x, which as we know, n factorial over k factorial times n minus k factorial on the bottom. Then we have x to the k, 1 minus x to the n minus k, and then times this coefficient here. Keep in mind, this is the only portion of this expansion that depends on f, but it does not depend on x, and that's actually quite useful to keep in the back of our mind for now. And here, this is the only part that depends on x, but it doesn't depend on f, right? So practically f is deciding the coefficients of this polynomial. And this is obviously going to be a polynomial of degree n. So the subscript of this function dictates the degree of that, right? And obviously, the closer and closer n is to positive infinity, the better and better this approximation is. And this function, Bnx, is sometimes called the nth Bernstein polynomial. So the nth Bernstein polynomial for the function f. And keep in mind, this only works on the interval 0, 1. All right? So regardless of the function you have, as long as you're continuous on the interval 0, 1, we can always approximate it to any degree of accuracy with a degree n Bernstein polynomial. But actually, the only thing that we really need is to observe that this is just a polynomial. It's a specific one, but it just is a polynomial. So we can always approximate any continuous on 0, 1 with a polynomial to any degree of accuracy that we want, restricted on the domain 0, 1. And you're like, well, what if I don't want to work on the interval 0 to 1? That's obviously understandable, and that's where the next theorem comes into play, right? So theorem 3, and this is the superstar. So this is the Weierstrass Approximation Theorem, and it says the following. So let's assume that D is equal to the closed interval AB. Let's assume that F has a domain of this closed and bounded interval. And let's assume that F is continuous on this domain. Then, if epsilon is greater than 0, if that's not an epsilon, that's a there exists. So if epsilon is greater than 0, then there exists a function p, and this p is a polynomial, such that the absolute value between f of x and p of x will be less than epsilon for all x in that closed and bounded domain. So here we have an arbitrary closed and bounded domain AB. Obviously, if AB is equal to 1, then that's just our Bernstein theorem. But it doesn't specify the Bernstein polynomial here. It just says there exists a polynomial. But the Bernstein polynomial is a polynomial. So 0, 1 interval of the Weierstrass can be easily proven with the Bernstein theorem. But this says that regardless of whatever closed interval you're working on, you can always approximate it with a polynomial of any degree accuracy that you want. All you have to do is just make n get arbitrarily large. And then Bnx, if you're on 0, 1, will converge to your function f. So let's actually work through an example on 0, 1 to sort of see how that would work. So let's take our function on the closed interval 0 to 1 with r, and let's assume that we're working with f of x is equal to, let's choose sine x again. So what are we going to have? So our second Bernstein polynomial, so this is our degree 2, because we did a quadratic before, but let's do a quadratic with the Bernstein approach. So this is going to be equal to the sum from k is equal to 2 of n choose k, and technically n is going to be equal to 2 here, so let's just write it as 2 choose k times x to the power of k times 1 minus k to the 2 minus k times the sine of k divided by 2. So this is going to be our second Bernstein polynomial for the sine function on 0, 1. So if we expand that, what do we get? So we're going to have 1, so that's our first binomial coefficient, times x to the power of 0, 1 minus x to the 2 minus 0 times the sine of 0 over 2. And then we're going to have 2 times x to the power of 1 times 1 minus x to the power of 2 minus 1 times the sine of 1/2. And then we're going to have 1, our last coefficient, times x to the power of 2 times 1 minus x to the power of 2 minus 2 times the sine of 2 over 2. Now, if we simplify this a little bit, notice that we have a sign of 0 here. That's obviously equal to 0, so this first term can completely eliminate. So we're going to have that our second Bernstein polynomial for the sine function on 0, 1 is just going to be equal to these last two terms, which is just going to be equal to 2x times 1 minus x, so 2x, 1 minus x to the power of 1, times this coefficient sine of 1/2. And then we're going to have, so 1 minus x to the power of 0 is going to be equal to 0 times x squared. It's going to be equal to 1. And then we're going to be just left with x squared times the sine of 1. Right? So this is going to be our approximation for the sine function as long as x is in between 0 and 1. And you could be asking, well, what if I don't want 0 to 1? Can I get any other interval, for example, a, b? Yes, all you have to do is just shift and scale this particular function using any preferably bijective scaling functions on your variable x. But that's more of a numerical analysis approximation theory thing. So we'll work on that another time. But keep in mind, if you do widen your interval to something else, your accuracy is going to decrease. It's going to decrease a lot because you're covering a larger interval with the same exact degree. So if you want to sort of get around the scaling feature, you probably want to sort of do, an approximation on 0, 1, an approximation on 0, 2, approximation on 2 to 3, 3 to 4, 4 to 5, and so on, then unionize those things together. Right? But the most important thing to notice here, this is just a degree 2, and you can always go a little bit higher. Because the main part about what the Bernstein theorem and also the Weierstrass theorem says is the following, that as you increase the degree of your degree n polynomial, you're actually going to get your function f. And that's obviously on 0, 1 for the Bernstein approach, or it's going to be equal to AB for your generalized Weierstrass approach. And that's practically it, right? So regardless of the continuous function you have, you can always approximate it to any degree of accuracy that you desire with a polynomial of degree n, right? So if you want higher accuracy, just choose a higher value of n. So I hope you enjoyed this video, and I'll see you in the next one. Take care.